So the reaction rate is given R1, R2 because there are two reactions. See? There are two reactions, so R1, R2, and rate constant. Reaction rate constant is also given in Arrhenius general form, Arrhenius equation. So if you see K1, K2, A times or K times e to the minus E over RT. E in this case is in Arrhenius equation is activation energy. So all values are given, and if you look at here, when we express reaction rate R1 and R2, we use a negative sign in front. Okay, why we use a negative sign?
Because it's going out of the constant
Reactant and product.
or like reactants and products of you have less reactants than
Exactly. Can anyone rephrase what page is said? Look. No? Anyone? Ryan?
The last time they equations being negative.
Huh?
The last time they equations being negative, because you have a negative left.
So why, if you look at here, my question was, we have reaction rate R1, reaction rate R2, because there are two reactions. See? Ethanol react with acetic acid to produce ethyl acetate and water. But reverse reaction also happens. Ethyl acetate react with water, produce ethanol and acetic acid. So we have two reactions. But when we express reaction rate, we use this negative sign. Page already explained that, but I'm looking for reference of what page explained. Why we use this negative sign to express reaction rate? Hey, you want to read yourself? Oh, you want to read? Yes.
Is it because reactions take energy to actually complete?
I tend to speak louder.
Is it because reactions usually take energy to complete?
Energy.
Therefore it's negative. Because you're losing energy during the reaction.
Anyone else?
Because the reactants concentration is
Wonderfully. That was all I was looking for. Really. What page is that? Page is okay. Baby, can you speak louder to everyone?
it means the concentration of the reactants is decreasing.
Exactly. Concentration is important. So why we use this negative? That means by reaction, ethanol acetic acid concentration decrease, but of course the ethyl acetate water concentration is increasing. That's why to express that the decreasing of concentration in reactant, we use that the negative sign. Yes? Okay. As I mentioned, there are 7 reactors available in Aspen, but we will just look at 5 different reactors. There is called stoichiometric based reactor, R story. As you can see, stoichiometric based reactor is a specified conversion reaction. And Gibbs based reactor, R Gibbs, rigorous reactor that includes phase equilibrium using Gibbs free energy minimization. So if Gibbs free energy go to 0 or a small low number, then the reaction becomes stable. Yes? If Gibbs free energy is negative, what does that mean? Gibbs free energy negative. Chase.
Not spontaneous.
The reaction is spontaneous. That's what I mean. Gibbs free energy is negative. Reaction is spontaneous. Gibbs free energy positive. Reaction is non-spontaneous, which requires more energy to work. That's what the Gibbs free energy tells us. Gibbs free energy becomes zero or close to zero, means the reaction becomes stable. Okay? Yes? Yes or no?
Yes.
Yes. If enthalpy is negative, what does that mean then? Enthalpy is negative.
Then it's exosomic.
Enthalpy is negative is exosomic.
Yeah.
Enthalpy is positive endosonic. Okay? Gibbs free energy negative spontaneous. Gibbs free energy positive non-spontaneous. RCSTR. CSTR. Have you heard about CSTR? Yeah, it's called continuous stirred tank reactor. Most commonly used in industry. Why? We want to make our product continuous. Continuous. CSTR. Very importantly. Most commonly batch reactor. We input, we react for certain time, so it's not continuous. That's called batch reactor. Continuous, the flow is continuous. Continuous stirred tank reactor, CSTR, is rate controlled reaction based on specified kinetics. R plug flow reactor, okay? Vigorous plug flow reactor is rate controlled reactions based on specified kinetics. And our batch reactor, batch and semi-batch reactor is known reaction kinetics. So we will look at these 5 different reactors today. Stoichiometric-based reactor, Gibbs reactor, CSTR reactor, plug flow reactor, batch reactor. Okay, is it clear? Process distribution or flow sheet looks simple. We have ethanol, acetic acid, and then we are going to use 5 different reactors to produce ethyl acetate. And the byproduct is water. And if time allows, maybe we can look at this SRK equation of state model, how to find the specific volume of one butene at the 415 K and 208 K if time allows. But let's look at it, these reactors first. So, if you go Aspen, specialty chemical is metric unit. How is your Aspen study going? Good. Jace said he loves it. Jace said, he confessed, oh, Dr. Kim, I love Aspen. Anyone else? Anyone else? Chase? Not yet? Spend more time. Jace worked for all night long. He didn't speak to some question all night long. What component do you have, Jace then?
See, ethanol,
One good. See?
acetic acid,
Okay. Ethanol, acetic acid, continue. Please continue.
that's all. This,
Ethanol, acetic acid, those are input. We produce ethyl acetate and water. So the component will specify 4 different components. Reactant and product. Yes? Now if you, as I said, you can use only up to 8 characters. So acetic acid, ethyl acetate are not found. So let's find out acetic acid. Acetic acid, 2 syllables. You use hyphen, easy to found. Use hyphen, acetic acid, 2 syllables. Okay, ethyl acetate, 2 syllables. I use hyphen, as the easily found. If it's not, you can go find, you can find out it. Let's go next, specify thermodynamic property method. So if I go method assistant, let's look at it, method assistant. okay, we are dealing with acetic acid, which is carboxylic acid. So maybe I can choose a special and such as acetic acid in the mixture. So if you go look at here, you can see method assistant recommend NRTL paid opener method or Wilson Nagel method. So can you see it's very small character, but as I said, method assistant recommend two different methods. NRTL paid opener or Wilson NTH method. So I can choose either one. So if you look at NRTL, HOC, or NTH, either one. Yes. Okay. Whenever you see estimate missing parameters, yes. So next, make sure table generation completed. We can go simulation environment. If you look at here, the bottom model pelvic, we are working on reactors today. So if you click reactors tab, as you can see, we have 7 different reactors, very similar, but we will look at it 5 different reactors today. Since we are simulating 5 different reactors, I may use maybe one duplicate to facilitate our input stream. And I can choose R stoic reactor first, stoichiometric based reactor. So let's try to connect our stream, input stream. Now, okay, so I'll name it this one. This is one is for duplicate. Just duplicate our feed stream so that we don't need to create feed stream again and again. This is feed stream for stoichiometric based reactor. I will name it R stoic. Product from stoichiometric. Don't know what to do? Maybe I can click next button. Okay. Now the temperature, pressure, mole flow all given. So temperature is 70 degrees Celsius, 1 atm, and ethanol 180 kilomole per hour. Default is kilometer per hour. I just check the drop down arrow, change to mole flow. So ethanol 180 kilomole per hour, acetic acid 200 kilomole per hour. Now we are working on stoichiometric based reactor, R stoic. Okay. What is required? Temperature and pressure is required. And please make sure to check these valid phases. So if you go valid phases, the default is vapor liquid. Okay, I have this vapor liquid phase. And if you go next, you are working on reactions. You will pay attention to it. We are working on reactions. Okay, I will click new. We are working on edit stoichiometric new window. So if you look at here, we have 2 reactants or component, ethanol, acetic acid, react, and right hand side is product produce ethyl acetate water. Okay. Now if you look at this window, we still have some information necessary. It's called coefficient. What do you think we need to put here? Coefficient. Yeah. K values no. Cool. 1? Yeah, 1? Who said 1? Chase? Why I mean?
The stoichiometry is 1.
Well, yes, exactly. This coefficient is the stoichiometric coefficient. So if you look at our reaction, and if you look at our reaction here, ethanol react with acetic acid, produce ethyl acetate water, and stoichiometric coefficient, as you can see, is all 1. That's what can be coefficient. Yeah, yes, stoichiometric coefficient of the reaction. And as you can see, reactant, if you put one, it will take a negative one because concentration decreased by reaction. And product side, if you put one, it will take a positive one. This is the first reaction, but we have another reaction, second reaction. So we need to also define second reaction. But in first reaction, what else information is necessary? As you can see, you can choose molar extent. If you know the mole flow, you can choose the molar extent, or you can choose fractional conversion. So how do you know this fractional conversion? Or you can do Google search, or to get some reference. And you get some reference or Google search, and you can find out. What I found is about 70% fractional conversion of ethanol for the first reaction. That's what I found. You can do Google search for the reaction. Fischer esterification reaction. Now we have another reaction, reverse reaction, second reaction, which ethyl acetate reacts with water, produce ethanol and acetic acid. Stoichiometric coefficient is also all 1, and fractional conversion I found is 0.25, 25% of ethyl acetate. Easy? And we can go next. Looks like, okay, everything is fine. And reset just in case. Let's look at it, our simulation results. No worry, no error. And then we can go sim summary because we are interested in how much ethyl acetate is produced from this reaction. So I can look at it. This cell produced 126 kilomole per hour of ethyl acetate is produced then. Easy? Alright, let's go quickly then. Then I'm going to install RGIS. Okay. Same thing, I can connect input and output. Please practice as I show you. Then you understand in every reactor. RDIPS basically defines only temperature pressure. So we will use the same pressure, same temperature. That's all. We can see our product from RDIPS reactor got about 160 kilomole per hour. Okay? Next one, let's look at it. CSTR reactor. As I said, most commonly used in industry. So let's look at it. CSTR. And what is required? If you click next, we can choose the same 180 and 70 degrees Celsius, valid phases, vapor liquid. Okay. Reactor volume may be 1 cubic meter. Okay. And then if you click next, we have to define reactions. When you use CSTR reactor, okay, we have to define reactions from reaction folder. So if you go navigation panel, we have a reaction folder. Please go reactions here, reaction folder. And we have to create our new reaction and select the type. There are different types. We use power law typing. So please choose power law. And same procedure. We can define two reactions here. Okay? Now I can request here ethanol, acetic acid, ethyl acetate, water. We know stoichiometric coefficient. Now, what do you think the exponent will be here? Exponent. Respond.
Do what? I didn't hear you.
So if you look at this window, okay, we finished the coefficient, that's the stoichiometric coefficient, but there is called exponent here. What do you think this exponent means?
If it's like not a first order reaction.
Wonderful. Oh, see, that's already know. Is it first order reaction or second order reaction? Our case is first order reaction. So at least you have to put exponent in reactant part. First order or second order reaction. Good. I give you all information. And if you look at your reaction type, it's called kinetic or equilibrium. We will look at it later more detailing. Today we have kinetic information, so we use kinetic reactions. No? And we have another reaction, reverse reaction. So I will throw ethyl acetate water here. Produce ethanol and acetic acid, stoichiometric coefficient, and first order reaction. Now if you look at here, we are working on CSTR reactor, stoichiometry and kinetic. So if you go here, kinetic, okay, can you see where? Let me do exercise. If you click in this drop down arrow, we have two reactions. And we are working on the first reaction. Reacting phase, liquid, vapor, different phase. Our reaction is liquid phase. Base phase is reaction basis or catalyst. If you have catalyst, catalytic phase, different reaction basis or catalytic basis. Now, if you look at here, T now or initial temperature is not specified in our case, so we can use this format. Okay? And our reaction kinetic is given. So in that case, that K value, I need to show you, let me show you. Just in case, who didn't get this? Okay, so we have this K reactor rate constant values are given, activation energy is given. We are going to use that information for that reaction kinetics. So if you look at K, what's the value here is 1.9 80. Okay? And activation energy is 5.95 e to the 7. And unit is joule per kilogram. So this will pay attention to the unit, joule per kilogram. Because we have two reactions, you click drop down arrow for second reaction, K is 5 e to the 7. Okay? And activation energy 5.95 e to the 7 joule per kilogram. Okay? CSTR, that's what we are working on. Let's go. If you click next, we have to define this reaction. We define our reactions under reactions folder. So we can choose what we define in the reactions folder. Then we can run the simulation. Then check your results. So we got product using CSTR reactor. Yeah, let's go quickly. R plug, very similar to CSTR. So we can go quickly now. We are working on plug flow reactor. Have you heard about plug flow reactor?
Yes.
Yes, of course. Good. So we are working on plug flow reactor. Let's see how does it look like. Who is it there? No? So we have specified the temperature, so you can choose from drop down arrow Okay, we have temperature, so I use that information, which is 70 degrees Celsius. Then configuration, length, you just put any number here for simulation purpose. Phase, vapor, liquid. Reaction, we already defined R-1, so I can use same one. And you can check whether the result from plug flow react product. Yes. The last one we have batch reactor. So if you look at here we have R batch. So let's try to look at batch reactor. So namely interesting batch, R batch, and product stream batch. Okay, so what is required? If you click next specification, we are working on constant temperature, so I can choose constant temperature, 70 degrees Celsius, valid basis, always check the valid basis. Vapor, liquid, valid basis. Pressure, given 1 atm. Now, if you look at the reaction, you find the reactions, you can choose. Start criteria, we have criteria number 1, location, reactor, variable type, maybe time, how long, maybe stop value 1 hour. Just put any number here, just for your practice. Maybe choose 1 hour. Let's see, okay. No warning, no error. And we can see product stream from batch reactor. Yes, we got active acetate product. Yes, yeah.
Our CSTRs,
These values we cannot compare because we use the arbitrary numbers. So we should get similar numbers, but not exactly the same, because as I said, I chose arbitrary number. For batch reactor, I chose like 1 cubic meter of size, all those sizes, right? Yes, so you will get similar result. You mean CSTR we got bad, you mean, oh, this one is too bad? Let's try to fix. Oh, good observation. So CSTR, what we have done wrong?
You did, yeah, cubic inch.
Oh, it's cubic inch? Okay, that's the problem. But Ian is good observation. I appreciate that. So I didn't pay attention to that result actually. Let's look at it now. Happy? Yeah. All right. Oh, good. What's the key point here? What we are talking about?
different types of reactors.
Different types of reactors. And then what is the key point I'm asking you? Practice it today. Look at it today. You try to look at tomorrow, you will forget what I showed you. So just to get familiar with different reactors, 5 different reactors and so on. Any questions? No? Who does not promise to look at it today, reactors? Let's look at this question. Now we are a little familiar. What is this thermodynamic property method? NRTL method, Unipeg method, Wilson, ideal, SRK method. Now you know SRK? Equation of state-based method, SRK. SRK, so often, Bradley Cohen, person's name, or the researcher's last name. 3 people worked together to develop this equation. That's called SRK method. How Aspen find out those thermodynamic properties or transport properties? kinetic properties simply using this base equation. It's called SRK method. Yes? So when we say SRK, use that equation. Variance of ideal gas law. And in this equation, where A variable, B variable are defined, the equations are given, and temperature use K, Kelvin, pressure ATM, volume, specific volume, liter per mole. Unit looks like unit are consistent. The gas constant is given, critical temperature, critical pressure is given. Now, by using SRK method, means by using this SRK equation, find specific volume of one routine at 415 K and 208 atm. Anyone, how can you find specific volume of one routine? Look it up. How? No, we have to use this equation. We have to use this equation. So if you look at here, we got critical temperature, critical pressure, gas constant R, okay, and A variable, B variable. We can find out, but as you can see, we are looking for this specific volume on denominator, but the volume shows up three different areas. Not easy.
Plug it into Wolfram Alpha.
Plug in Wolfram Alpha, you can find it. Yeah? Or anyone else? Can you use MATLAB?
Yes.
No?
Yes.
You
Huh?
can do a lot of things.
No, put it up. Yes. You can use Wolfram Alpha, or can you use MATLAB? I recommend you use MATLAB. Why? Behind the aspen, there are million lines of code. And more than million lines of code to find out these properties. Very similar to MATLAB. So I will show you how to use MATLAB. But I know you guys are experts, so please help me. So we have R, let's see. R is what? 0.0825. We have TC, 420. We have PC, 400. We have temperature looking for at 415. Pressure looking for 280. A variable is defined, so I can use A is 0.42748 times R squared times PC power T 2.5 divided by PC. We have B variable 0.08664 times R times PC divided by PC. We are looking for B, but if you think about, so let me write down the equation. SRK is P is equal to RT over B minus B minus A over B plus B plus SRK equation. Whenever you have this kind of equation, we are looking for this volume and certain temperature and pressure. Yes? You change it to this format. Fs is equal to 0. What does that mean? We are looking for volume, specific volume, should be equal to RT over B minus B minus A, B plus B, square root of T, send this P to the right hand side, minus P is equal to 0. Yes? Good. So I am going to find out f is equal to 0. Nobody remembers? F0. No, F0 is not F0. So I'm looking for you F0 function. Function handles two sides of this function. And I have equation r times t divided by v minus b minus a divided by b times b plus b times square root t minus p, and our initial guess, you can put any value, maybe 1. Initial guess. That's the F0 function available in F0. So, if I learn this one, we are looking for specific volume of one routine at 450K 200 ATM. Let's find out. Is equal to 0.1355 liter per mole. Did you choose a problem? Did you find out the answer? No, not
I
yet.
saw wrong.
Okay. What is the beauty of Redlet in background Aspen code? As I said, there are more than 1 million lines. You can display or you can do more simple analysis. Display maybe TK, and then we are looking for volume beta O mode. And if I display this one, can I put temperature range? And then I can find the specific volume as a function of temperature range. So I can just for T is equal to, maybe we can vary 400 to 500. Okay. Then I found out specific volume as a function of temperature range, and I can do everything there. First I can observe that. The other thing.
It just says F print. For the function handle, or whatever, it just says F print. You need to have F print F.
With F, wonderful. Thank you. So we can get specific volume of one routine as function of temperature. Yes? So we were looking for 415K was 0.1333 something. If you plug, it becomes easy to look at it. So if you plug, I have two small size, I can write small size. And I make it larger marker size. How many? 30? 20? Let's see. So as I said, in background, ask many, there are more than million lines of code to find out these kind of properties as a function of temperature, as a function of pressure, we all find out different properties. Transport properties, we know how many bunch of properties. Huh? Same approach. How can you improve? Hybrid. We are looking for specific volume, which is one good thing. Specific volume of one good thing. Unit is meter per mole versus temperature. Okay. Okay. Can I make the pump size? X label. X label, what's X label? Temperature. Pump size, 20. Y label. This specific volume. Meter per mole. Let's see. It's better? You may always spend a little more time, maybe look better, right? Please. That's what the chemical engineers do. Come on. Point the size. 18. Let's make sure. Ryan. Steve. Jacob. Jackson. Tyler. Joe. Don't be late, guys, huh? Don't be late, please.